The second objective in this topic, rationalize denominators having two terms. Let's look at -2 over 2 plus radical 6. We want to rationalize this. Your first instinct might be, by the way, this is wrong. Don't write this down unless you're going to like put arrows at it and say wrong. Hey, radical 6 over radical 6, that's worked before. But while that might get rid of multiplying by this, what's actually happening is that we're distributing. So you would end up with 2 radical 6 plus 6. You've taken care of not having a radical on the bottom right, but you've given yourself a radical on the bottom left. Hey, you kind of realizing why I was talking about what makes radicals go away? Hopefully your spidey sense is tingling. Your next instinct, which would also be wrong, might be, well, if multiplying the radical by itself got rid of the radical, I'll just multiply this by itself. That won't work either because that's squaring a binomial. And we just looked at the fact that that would get rid of the radical at the beginning and the radical at the end. But it's going to be a 3-term thing that still has a radical in the middle. And while this will simplify to 4 plus 6 is 10 plus 4 radical 6, it does not get rid of the radical. So we try again. Squaring isn't going to do it. Well, that's why we discovered the fact that multiplying by the conjugate, if we have a plus radical 6, if we make that minus radical 6, that is a difference of squares. 2 squared minus radical 6 squared. And that's 4 minus 6. And that's -2. Let's figure out what the top is. If we're multiplying by 2 minus radical 6 on the bottom, since we're multiplying by 1 overall, that form of 1 is 2 minus radical 6 over itself. We're distributing on the top. -2 times 2 is -4. -2 times negative radical 6. Negative times negative is positive 2 radical 6. So -4 plus 2 positive radical 6. We can factor a -2 out the front. That would leave us with 2 minus radical 6. Is that right? -2 times 2 is -4. -2 times... Oh, look, it's the same form. I factored it right back out. And why did I factor it right back out? Well, there's a -2 on the bottom. If I take this -2 from the top, I can cancel those -2's, and my answer is just going to be 2 minus radical 6. Not only did I rationalize the denominator, I was able to get rid of the denominator entirely. So I can see you leaving the answer maybe like this. -4 plus 2 radical 6, and it was over -2. I can see you leaving it like that. That would be like not reducing a fraction all the way. And if you don't factor out the -2, then you at least have to be careful to split up -4 over -2 plus 2 radical 6 over -2. If you're dividing by -2, you can't just do one or the other. It has to be both. Why? How would you add these fractions? There's a common denominator. So I would keep the common denominator and add the top. Well, look at the previous line of work. Keep the common denominator, add across the top. Splitting is what has to happen because it's adding the fraction in reverse. I've said before, it's important to know how to work with fractions because later on, the rules are going to make sense because they're just the fraction rules. If you wanted to rely on calculators or something like that with fractions in the past, you're going to have to relearn how to do all of this. That's why it's important to know how to add fractions by hand, because then this step is natural to you. You don't have to wonder, why did he do that? You know why I did that, because that's how you add and subtract fractions. And then from here, negative divided by negative is positive, plus positive divided by negative is negative, plus a negative is subtraction. 2's cancel, 2 minus radical 6. So that's how you rationalize when there is a binomial on the bottom. When there's more than one term, you have to use the conjugate to get the difference of squares. Let's do one more of these. Let's rationalize 8 over 3 plus radical 5. Well, 3 plus radical 5 means 3 minus radical 5 is what gets rid of it. Over itself, distribute on top, FOIL or difference of squares on the bottom. 3 squared minus radical 5 squared. On top, 24 minus 8 radical 5, distributing that 8. So 24 minus 8 radical 5 over 9 minus 5. That's 24 minus 8 radical 5 over 4. Let's just split it up. Let's not worry about factoring. 24 over 4 minus 8 radical 5 over 4. That gives us 6 minus 2 radical 5. This 6 minus 2 radical 5 is exactly the same as 8 over 3 plus radical 5. But we don't want that radical 5 in the bottom. We rationalize, we get our answer as 6 minus 2 radical 5. The third objective in this topic, rationalize numerators. The things we just did to get rid of the square root in the denominator, we can do the same things to get rid of the square root in the numerator. So for example, if we have radical 12/7, that's radical 12 over radical 7. And to get rid of the radical on top, we would multiply by radical 12. Over radical 12, of course. Radical 12 times radical 12 on top gives us 12. On the bottom, we have radical 7 times radical 12. That's radical 7 times 12, radical 84. 84 is 4 times 21. Radical 4 times radical 21 would be 2 radical 21. Finally, 12 divided by 2 is 6. So that's a 6 on top, left with a radical 21 on the bottom. It's okay that the radical's on the bottom here because the point was to rationalize the numerator. Make sure the numerator is the one that doesn't have the radical. Let's rationalize the numerator for cube root of 9y over 7. Give the cube root to the top and the bottom. There are no cubed factors of 7. There are no cubed factors of 9, as annoying as that is. But 9 is 3 squared. If we had 3 cubed, and if we had y cubed, that would cancel the cube root out. 9 is 3 squared, so we need one more factor of 3. And to get to y cubed, we need 2 more factors of y. That's why we're multiplying by the cube root of 3y squared. 3 squared times another 3 gives us 3 cubed. Y times y squared gives us y cubed. And it has to be a cube root because we need it to be able to multiply with this cube root. And it's over itself because we can only multiply by 1 and not change the value. On top, that does give us the cube root of 3 cubed y cubed. That leaves us with 3y on the top. On the bottom, cube root of 7 times cube root of 3y squared. We can multiply the 7 times the 3 and get 21y squared. So 3y over the cube root of 21y squared. Rationalize the numerator of the square root of x plus the square root of y over the square root of x minus the square root of y. We want to get rid of the radicals on top. Since the top is plus, the conjugate will be minus. Let's multiply by the square root of x minus the square root of y over itself. This is 2 special formulas. On top, we set up the difference of squares. On bottom, we set up squaring the binomial. But let's act like we don't know the special formulas. Let's just go ahead and FOIL on the top and FOIL on the bottom. On top, x is what we get when we multiply radical x times radical x. So first, radical x times radical x is x. Outer radical x times negative radical y, negative radical x times radical y. Inner, positive radical y times positive radical x, positive radical x times positive radical y. Last, positive radical y times negative radical y is negative y. The outer and the inner, it's a minus term and a plus term. They will cancel each other out, just leaving us with x minus y on top. On the bottom, radical x times radical x is x. And then minus radical x radical y, minus radical x radical y again. And then minus times minus is plus. Radical times radical cancel out, just leaves us with y. So here, instead of the outer and the inner canceling, there's 2 of them. So there's minus 2 of the radical xy's. Now let's see this without the multiplication dot. So combining the radicals where we can. Like I said, the top, the radicals cancel out, leaving us with x minus y. On the bottom, there's two of them, so minus 2 radical xy. And if you used the special formula, you jumped straight to that, most likely. That's it for this topic. The topic is radical equations and problem solving. The first objective in this topic is solve equations that contain radical expressions. We're going to use something called the power rule. If both sides of an equation are raised to the same power, then all solutions of the original equation are among the solutions of the new equation. That doesn't mean the solutions are the same, though, so we definitely need to check our answers. Let's solve radical x plus 1 equals 5. Well, we're going to go ahead and square both sides, because squaring will get rid of the radical. The radical squared is x plus 1. 5 squared is 25. Now subtract 1 from both sides, we get x equals 24. Check in the original equation. 24 plus 1 is 25. The positive square root of 25 is positive 5. It is true. Our answer checks. So our strategy in all of these is if we see a radical, get it by itself on one side and then square both sides to get rid of it. Repeat until all of the radicals are gone. Isolate the radical. Raise each side of the equation to whatever power gets rid of the particular radical. Repeat as needed. And don't forget to check. It's not optional on these. So if we had the square root of x minus 1 equals 0, we don't want to square both sides yet because that's going to be overly complicating things. It won't get rid of the radical. We got to get the radical by itself first. So add 1 to both sides. Radical x minus 1 equals 1. Now we can get rid of the square root by squaring both sides. The square and the radical cancel each other out, just leaving us with x minus 1. And 1 squared is 1. Add 1 to both sides to get x equals 2. We check. Take the 2, plug it into the original equation. Square root of 2 minus 1 is the square root of 1, is 1. Minus 1 is 0. That is true. So our equation is x equals 2, our solution. Another one. Well, here we don't have the radical by itself yet. We can subtract 2x from both sides, though, to get the radical by itself. Now we want to square both sides, being careful when we square the right to FOIL with itself or use the special formula for multiplication. Square the first minus twice the first times the second plus square the second. 64 minus 32x plus 4x squared. It's not 64 plus 4x squared or 64 minus 4x squared. There is a middle term that we get from the outer and the inner of foiling with itself. On the left side, the square and the square root cancel each other out, just leaving us with x plus 1. At this point, get everything on one side, 0 on the other. Factor and solve. Check our values of 3 and 21/4. If we plug 3 in, 6 plus radical 4 is 6 plus 2. That's 8. That's true. If we plug 21/4 in, that's 42/4, which is 21/2, plus the square root of 21/4 plus 4/4 would be the square root of 25/4, which would be 5/2. 21/2 plus 5/2 is 26/2. 26/2 is 13. 13 does not equal 8. It is a false statement. So 21/4 does not work as a solution to the equation. Only x equals 3. Let's solve this one. Y plus 5, the square root of that, equals 2 minus the square root of y minus 4. We have two radicals. One of them is already isolated, so let's go ahead and square both sides, being careful to FOIL the 2 minus radical y minus 4 with itself properly. On the left, the radical goes away. Radical squared just leaves us with y plus 5. On the right, we have first 2 times 2, that's 4. And then outer will be minus 2 radical y minus 4. Inner will be minus 2 radical 4. Negative 2 of them minus 2 more is negative 4 of them. And then last will be negative radical times negative radical. That's positive. The radicals cancel each other out, leaving us with y minus 4. Or you could use the special formula, square the 2, subtract 2 times the first times the second, add, square the second. Simplify 4 minus 4, subtracting y from both sides, leaves us with 5 equals negative 4 square root of y minus 4. Divide both sides by negative 4. Negative 5/4 equals that radical, and that's what we've been working towards ever since we got this being the only radical left, getting the radical by itself. Why? So we can square both sides again. That gets rid of the last radical. Negative 5/4 squared is positive 25/16. Radical y minus 4 squared gets rid of the radical, leaves us with y minus 4. To get the y by itself, we want to add 4 to both sides. 4 is 64/16. 64 plus 25 is 89/16. 89/16. So we have our answer, our potential answer of y equals 89/16. We want to check that value. Five is 80/16. 80 plus 89 is 169/16. Square root of 169 is 13. Square root of 16 is 4. So the left side is 13/4. On the right side, 4 is 64/16. 89 minus 64 is 25/16. Radical 25/16 is 5/4. We have it to 2 minus 5/4. 2 is 8/4. 8/4 minus 5/4 is 3/4. 13/4 does not equal 3/4. That is false. We did all of that work for our only answer to not check. So there's no solution. This time we have two radicals and they're both on the same side. We can't square both sides until we have one of the radicals by itself. So I'm going to add the square root of 3x plus 4 to both sides. That gives me radical 2x minus 4 by itself on the left. On the right, negative 2 plus radical 3x plus 4. Square both sides. That gets rid of the square root on the left, 2x minus 4. On the right, square the first. Negative 2 squared is 4. 2 times the first times the second. 2 times negative 2 is negative 4 times the square root of 3x plus 4 plus square the second. The square root squared leaves us with 3x plus 4. That's also what you get if you FOIL with itself. Either way, you need 1, 2, 3 pieces. Combining like terms, 4 plus 4 is 8. Subtracting 8 from both sides. Subtracting 3x from both sides. We get this negative 4 radical 3x plus 4 by itself. Simplifying the left, 2x minus 3x is negative x. Negative 4 minus 8 is negative 12. Since we just have the single term, you might be thinking, should I divide by negative 4? You don't have to. This is close enough to by itself. Let's just go ahead and square both sides, rather than divide by negative 4 and involving a fraction. Be careful when you square negative x minus 12. You get x squared plus 24x plus 144. Be careful when you square the negative 4 square root. Negative 4 squared is positive 16. The square root squared cancel each other out, leaving us with the 3x plus 4. That 16 is multiplied by the entire 3x plus 4, because that negative 4 was multiplied by the entire radical. And 16 times 3x plus 4 equals 48x plus 64. So we have x squared plus 24x plus 144 equals 48x plus 64. Subtract 48x from both sides. Positive 24 minus 48 equals negative 24x. And then 144 minus 64 is positive 80. Everything on one side, 0 on the other. Factor. Numbers that multiply to positive 80 and add to negative 24 are negative 20 and negative 4. And then solve x minus 20 equals 0, x minus 4 equals 0. We get x equals 20 or x equals 4. We have to check both. When we check 4, plug it in. 8 minus 4 is 4. Radical 4 is 2. 12 plus 4 is 16. Radical 16 is 4. 2 minus 4 is negative 2. That one's true. 4 works. If we plug 20 in, 2 times 20 is 40, minus 4 is 36. So that's radical 36. Minus 60 plus 4, radical 64. That's 6 minus 8, which is also negative 2. Both 4 and 20 work. The solutions are x equals 4 or x equals 20. After all those, something nice and small. Maybe this will be simple. Maybe there won't be any tricks. Radical 5x equals negative 5. We're going to square both sides because we have the radical isolated. That's going to leave us with 5x on the left and positive 25 on the right. Divide both sides by 5, we get x equals 5. When we substitute that back into the original equation, we get radical 5 times 5, or radical 25 equals negative 5. Remember, while it's true that negative 5 is a square root of 25, when we see the symbol, when we see the radical, that's the positive square root only. So this would say 5 equals negative 5, which is false. So the solution is the empty set. There is no solution.
We have a power property, which basically says any solution to the equation P equals Q is also going to be a solution to the equation P to the N equals Q to the N. It does not say that these equations are equivalent. It only says that each solution of the original equation is also a solution of the new equation. So our strategy to solve equations involving radicals, or really powers, is that we do something on one side and also do it on the other. To get rid of square roots, we square. To get rid of squares, we square root. Let's take a look at example 4. It's going to make a lot more sense when we see this in action. X minus radical 15 minus 2x equals 0. So first, we want to get this radical by itself. So we're going to start off. Oh, look at that. We have 0 on one side. Let's just add the radical 15 minus 2x to the other side. We're going to undo this square root by squaring both sides. So x squared equals 15 minus 2x. Now get everything on one side Add the 2x, subtract the 15, get 0 on the other. Factor. Numbers that multiply to negative 15 and add to positive 2 are 5 and negative 3. So x equals negative 5, x equals positive 3. We want to check our answers all the time in radical equations. So, we're going to check this twice. Once for x equals negative 5, once for x equals 3. If we plug in negative 5, we get negative 5 minus radical 15 minus 2 times negative 5 equals 0. Negative 5 minus 15 plus 10 equals 0. Negative 5 minus radical 25 equals 0. Negative 5 minus 5 equals 0. Negative 10 equals 0. Well, wait a minute, that's not true. It's not true. X minus 5 is not a solution. Try it with 3. (15 minus 2 times 3 equals 0. 3 on the outside here. 3 minus 15 minus 6 under the radical equals 0. 3 minus radical 9 equals 0. 3 minus 3 equals 0. 0 equals 0. Check. So x equals 3 is our only answer. Let's look at example 5. Solving an equation containing two radicals. Radical 2x plus 3 minus radical x plus 1 equals 1. We want to get one of the radicals by themselves. So I'll just keep this radical 2x plus 3 on the left, and I will add the other one over. 1 plus radical x plus 1. Now that we have a radical by itself, square both sides, but be careful. Gives us 2 plus 3 on the left, and we have to FOIL or use the formula for squaring on the right. Square the first one. 1 times 1 is 1. Outer and inner. 1 times radical x plus 1 plus 1 times radical x plus 1 gives us 2 radical x plus 1s. Plus, if we square radical x plus 1, we get x plus 1. So this is why we worked on squaring things like this in the radical section. Now here's the thing. When you have two radicals in the equation, you're going to get to a point where you still have a radical left because of how we square this. So once we combine all our like terms, 2 plus x plus 2 radical x plus 1. 1 plus 1 is 2. We're then going to get everything on one side, leave the radical on the other. So subtract the 2. Subtract the x. X plus 1 equals 2 radical x plus 1. We don't have to divide by 2 everywhere because we can just go ahead and square now. If it was 2 plus the radical, we wouldn't be able to just do that. That would cause us something with a radical still. But 2 times the radical, we can do that. X plus 1 squared is x squared plus 2x plus 1. 2 squared is 4. Radical x plus 1 squared is x plus 1. We still have to multiply those together. So distribute 4x plus 4. Get everything on one side, 0 on the other. So subtract 4x from positive 2x. Subtract 4 from positive 1. The numbers that multiply to negative 3 and add to negative 2 are negative 3, positive 1, which means x equals positive 3, and x equals negative 1. We now have to check that in the original equation. Which was radical 2x plus 3 minus radical x plus 1 equals 1. So let's do this check. So radical 2 times 3 plus 3 minus radical 3 plus 1 equals 1. Radical 6 plus 3 minus radical 4 equals 1. Radical 9 minus radical 4 equals 1. 3 minus 2 equals 1. 1 equals 1. We're good. With the negative 1, radical 2 times negative 1 plus 3 minus radical negative 1 plus 1 equals 1. Radical negative 2 plus 3 minus radical 0 equals 1. Radical 1 minus radical 0 equals 1. 1 minus 0 equals 1. 1 equals 1. Both of these check. Both of these are in our solution set. We like how this one looks. Cube root of 4x squared minus 4x plus 1 minus cube root of x equals 0. You're probably thinking, what do you mean we like how this looks? We don't like how this looks. When we have 0 on one side and 2 radicals, it's so much easier. Because look what happens if I add this cube root over. 0 plus the cube root of x is just the cube root of x. We have cube roots isolated. How do we get rid of cube roots? We cube both sides. Cubing a cube root just gets rid of it. We have 4x squared minus 4x plus 1 equals x. Let's get 0 on one side, so subtracting x gives us 4x squared minus 5x plus 1. And we're going to factor this. Now, you've seen me do the AC method multiple times. You should know how to factor using the AC method at this point. I'm going to show another method which is going to work. So the first step is if we have a common factor in all the terms, we're going to have to factor that out first. In an equation, you factor it out, you divide by it. 0 divided by that number keeps 0 on one of the sides. Now, we still need to find AC. We still need the numbers to multiply to be 4 times positive 1. We need to multiply to be positive 4 and add to be negative 5. But we're going to be able to do something with just our binomials. So the numbers that multiply to 4, add to negative 5, are minus 4 and minus 1. What do we have here? 4x squared. So let's put 4x and 4x. Yes, I know that that's 16x squared, but bear with me. Our numbers, -4 and -1, we're going to put them right in. Nothing in common here, so we're not going to divide by anything. What do we have in common here? A 4. Let's divide by 4. So this is x minus 1 times 4x minus 1 equals 0. You don't believe me? Let's do the actual AC method, side by side. So we found the numbers that multiply to AC, +4, add to B, -5, that's -4 and -1. Use that to split up -5x into -4x minus x, -x minus 4x. Factor by grouping. Take out a 4x, we're left with x minus 1. Factor out a -1, we're left with x minus 1. X minus 1, 4x minus 1. Same thing. If we finish solving here, we get x equals 1, +1, and x equals +1/4. We need to check these. In the original, so in cube root of 4x squared minus 4x plus 1 minus cube root of x equals 0. We're going to check first x equals 1. So cube root of 4 times 1 squared minus 4 times 1 plus 1 minus cube root of 1 equals 0. Cube root of 1 is 1. 1 squared is 1. 4 times 1 is 4. Minus 4 plus 1. So this is the cube root of 1. Minus 1 equals 0. 1 minus 1 equals 0. 0 equals 0. This one checks. So x equals 1 is an answer. Let's do it again with x equals 1/4. Be careful. 1/4 squared minus 4 times 1/4 plus 1 minus the cube root of 1/4 equals 0. Don't panic. We're doing this with x equals 1/4. 1/4 squared is 1/16. 4 times 1/4 is 1, so minus 1 plus 1, and those cancel. Yes, I know we can't do anything with the cube root of 1/4. Be patient. 4 times 16 is 4/16, which reduces to what? 1/4. Cube root of 1/4 minus cube root of 1/4 is 0. 0 equals 0, checks. So our answers are both x equals 1 and x equals 1/4.
Let's solve 2t equals the square root of the trinomial 4t squared plus 4t minus 19. We have the radical by itself. Let's go ahead and square both sides. Two t squared is 4t squared. Square a square root gets rid of the square root. If we subtract 4t squared from both sides, those cancel away. We're left with 0 on the left equals 4t minus 19. Add 19 to both sides, 19 equals 4t. Divide both sides by 4. T equals 19/4. Three minus the square root of x plus 2 equals the square root of 3 minus x. We have a radical by itself. That's great. We can square both sides right away. We get a radical by itself. We can square both sides to simplify a bit. And the radical and the square undo each other. This just equals 3 minus x on the right. On the left, be careful because it's this times this. Foil it with itself. 3 times 3 is 9. And then we're going to have minus 2 of these things multiplied together. 3 times the radical x plus 2. That's the outer and the inner multiplied together. Last, square the square root, square this. It's plus x plus 2. So what I just did was take that times itself. First, outer, inner, last. Or use the special formula. Square the first minus 2 times the first times the second plus square the second. Let's clean this up a bit. This is 9 minus 6 radical x plus 2, not subtracting first. Order of operations says we multiply first. Nine plus 2 is 11. 11 minus 6 radical x plus 2 plus x equals 3 minus x. Do I do 11 minus 6 to get 5? Absolutely not. These are multiplied together because of order of operations. They cannot be separated. These are not like radicals. They cannot be subtracted. Let's get this radical by itself. I'm going to subtract 11 from both sides. I'm going to subtract x from both sides. That's going to give me negative 6 radical x plus 2 equals negative 8 minus 2x. And now I can square both sides. This won't be a problem. Let me move it up first. And I square this side. I square this side. Here, negative 6 times negative 6 is positive 36 times x plus 2. Over here, square the first. Negative 8 squared is positive 64. Minus 2 times negative 8 times 2x plus 2x squared. So I'll even write this as negative 8 squared for now. So again, same formula, square the first, minus 2 times the first times the second, plus square the second, or FOIL it with itself. You'll get 64 plus 2 times 8 is 16 times 2 is 32x plus 4x squared. And over here, distribute the 36, 36x plus 72. Okay. I'm going to move everything over to here. So first I'll have my 4x squared. Then I'm going to subtract 36x. Positive 32 minus 36, that's minus 4x. Positive 64 minus 72, that's going to be the opposite of 72 minus 64. I'm just doing that math off to the side, nothing you have to copy. That's 8. So positive 64 minus 72, that's negative 8. I can divide both sides by 4. X squared minus x minus 2. I need two numbers that multiply to give me negative 2, that add to give me negative 1. And then I'll be able to factor with x and x. These numbers are going to be negative 2 and plus 1. They multiply to give me negative 2. They add to give me negative 1. Minus 2 plus 1. So x minus 2 equals 0. X plus 1 equals 0. We get x equals positive 2. We get x equals negative 1. All of that work to a negative 1 are the answers.
Objective 2 in this topic is use the Pythagorean theorem to model problems. To review the Pythagorean theorem, if A and B are lengths of the legs of a right triangle and C is the length of the hypotenuse, then leg A squared plus leg A squared equals hypotenuse squared. Sorry, leg A squared plus leg B squared equals hypotenuse squared. Or A squared plus B squared equals C squared. C is the hypotenuse. The hypotenuse is the side of the right triangle that is directly across from the right angle. So find the length of the hypotenuse of a right triangle when the length of the two legs are 2 inches and 7 inches. Since we're dealing with a right triangle, we're going to use the Pythagorean theorem, a squared plus b squared equals c squared. The two legs are 2 and 7. Doesn't matter which is which. Let's let A be 2 and B be 7. Then 2 squared plus 7 squared is c squared. 4 plus 49 is c squared. 53 is c squared. Finally, we would need to take the square root of both sides to get from c squared to c. Since we're dealing with length, the negative square root doesn't make any sense. So just the positive square root. C would be the square root of 53 inches. Next example, find the length of the leg of a right triangle. Give the exact length and a 2 decimal approximation. Let's let A equal 2 meters and C equal 9 meters. So 9 meters is the hypotenuse. 2 meters is one of the legs. We're looking for the length of the other leg. So let's let A be 2 again. Let's let C be 9. And we get 2 squared plus B squared equals 9 squared. That's 4 plus B squared equals 81. Subtract 4 from both sides, B squared equals 77. And again, to get from B squared to B, we would need to take the square root of both sides. That leaves us with B on the left and the square root of 77 on the right. That would be the exact length, square root of 77 meters. And if we put that in a calculator, we can get a 2 decimal approximation of 8.77 meters. A surveyor must determine the distance across a lake at points P and Q as shown in the figure. To do this, she finds a third point R perpendicular to line PQ. If the length of PR is 320 feet and the length of QR is 240 feet, what is the distance across the lake? We want the distance across. From P to Q. PR is 320. QR is 240. So we were given the hypotenuse and a leg. Use the Pythagorean theorem to solve. The hypotenuse, C, is going to be 320. The leg we have, we'll let that be A, 240. We want to find B, the other leg. So A squared plus B squared equals C squared. 240 squared plus B squared equals 320 squared. That's 57,600 plus B squared equals 102,400. Subtract 57,600 from both sides, B squared equals 44,800. The exact distance would be the square root of 44,800, taking the square root of both sides, but a decimal approximation with the calculator to the nearest whole foot is 212. feet. And that's it for this topic. Number 1, find the square root, and we're going to assume that all variables represent positive real numbers. That instruction means we don't have to worry about the absolute value when we take the square root of x. So we have the square root of x to the 28th power, and we know that a radical takes an exponent of the form power over root. So the 28th power, it's the square root, so 28 over 2 gives us x to the 14th. Number 2, we want to simplify, and this time we're going to assume that all variables represent any real number. That means we have to be careful. When we take the square root of x squared, that's going to be the absolute value of x, because variables can represent any real number. We have the square root of 9x squared. We can split that up into the square root of 9 times the square root of x squared, which gives us 3 times the absolute value of x. Number 3. Use radical notation to write the expression, simplify if possible. We have 3x to the 5/8. Now, the 3 has nothing to do with this x to the 5/8. There's no parentheses combining the 3 with the x. So the 3 is off doing its own thing. We know a radical takes an exponent of the form power over root. In this case, power over root is 5/8. So the 5th power, the 8th root. So 3x to the 5/8 is 3 times the 8th root of x to the 5th. Number 4. Use the properties of exponents to simplify the expression, write with positive exponents. We have x to the 1/8 times x to the 7/8. We're multiplying, we have the same base, so we add the exponents. 1/8 plus 7/8 is 1 plus 7/8, which is 8/8, which is 1. So the power ends up being 1. We just have x to the first. X is our answer. Number 5. Simplify the radical expression. Assume that all variables represent positive real numbers, so we don't have to worry about those absolute value signs anymore. We have the square root of 200k to the 7th, q to the 8th. We can split this up. Square root of 200, square root of k to the 7th, square root of q to the 8th, and take each on its own. We want to find perfect square factors. And the largest perfect square factor of 200 would be 100. Square root of 200 is the square root of 100 times 2. Largest perfect square factor in k to the 7th is k to the 6th. K to the 7th would be k to the 6th times k to the 1st. And q to the 8th, we're going to leave as q to the 8th because that is a perfect square factor. Remember, even powers are perfect squares. So now split up the radicals we have now. Radical 100, radical 2, radical k to the 6th, radical k, radical q to the 8th. Then I'm going to rearrange these. So up first, we have the radicals that are of perfect squares, the 100, the k to the 6th, the q to the 8th, times the leftover ones, the radical 2 and the radical k. Now we can combine the radicals since they're all multiplication. Combine the perfect squares, 100 k to the 6th, q to the 8th. Combine the leftovers, 2k. And take the square root of our perfect squares. 100k to the 6th, q to the 8th is the square of 10k cubed, q to the 4th. We can't do anything with that radical 2k, so we're left with 10k cubed, q to the 4th times radical 2k. Number 6. Add or subtract. Once again, we're assuming all variables represent positive real numbers, no absolute value. We have radical 3a minus 7 radical 12a minus 2 radical 108a. In order to subtract these terms, we need to get like radicals. So we want to rewrite any of the radicals we can in simplified form. 12a can be written as 4 times 3a. 108a can be written as 36 times 3a. Those are perfect squares times 3a. Split up the radicals. Radical 3a minus 7 times radical 4 times radical 3a minus 2 times radical 36 times radical 3a. We can take the square roots of 4 and 36. That's 2 and 6. So now we have radical 3a minus 7 times 2 radical 3a minus 2 times 6 radical 3a. We can do this multiplication, the 7 times 2 and the 2 times 6, giving us radical 3a minus 14 radical 3a minus 12 radical 3a. One of them minus 14 of them is negative 13 of them. Negative 13 of them minus 12 of them is negative 25 of them. We're left with negative 25 radical 3a. As always, your answer choices might be, or will likely be, in a different order. But in this case, with these choices in this order, the answer is A. Number 7. We want to multiply and then simplify if possible. Again, we're assuming all variables represent positive real numbers, so no absolute values. In fact, we don't have any variables in this problem, it turns out. We're multiplying radical 3 times the quantity radical 21 plus radical 3. That means we need to distribute the radical 3 to both terms, radical 3 times 21 plus radical 3 times 3. Since we're multiplying the radicals, we can multiply underneath a single radical. This is radical 3 times 21 plus radical 3 times 3. 3 times 21 is 63. 3 times 3 is 9. So we have radical 63 plus radical 9. Radical 63 can be simplified as radical 9 times 7. Radical 9 is 3. So we have radical 9 times 7 plus 3 right now. Split these radicals up, so it's radical 9 times radical 7 plus 3, which gives us 3 radical 7 plus 3.